Okay, our next speaker is Professor Jonathan Price. John is a professor in Department of Geography at the University of Waterloo. John received his undergrad in geography from Trent University and master in civil engineering from Saskatchewan, and also PhD in geography from McMaster University in 1988. John's research is mainly focused on hydrological processes in wetlands, especially looking at the very small scale, important scale to watershed scale. And also John is interested to impact the wetland system by climate change or oil sand or mining. Okay, John. Yeah.
Thanks, Farouk. Well, actually, a lot of my work recently has been in the Alberta oil sands region, creating wetlands, which is why I've decided not to talk about it today, because I needed something to refresh my own mind. And I'm going to talk to you a bit about a project which is coming to a close up in the James Bay lowland. This is an area where I cut my teeth as a PhD student. My research was on coastal wetlands in the James Bay lowland. And while I was there, I had an undergraduate student who went on to do great things and has actually come to address us today. It was Mike Waddington. He was my field assistant there. And then a few years after that, well, maybe it was about 10 years ago now, we had a PhD student which we jointly advised, and he is now my colleague in geography, Rich Petrone. And next summer, or this summer I guess, Maria Strack from University of Calgary is coming to join us in geography. It's the CRC chair. She's a peatland scientist, and she was Mike's PhD student. She worked as a postdoc in my lab, so incest is alive and well in the peatland community. So I'm going to talk to you about the Victor Diamond Mine. This is a mine, the De Beers Mine, which is in Attawapiskat. It's in the James Bay, Hudson James Bay lowland down and through here. It's an area which is 90% peatlands, and what's not peatland is the rivers, and there's a few bedrock outcrops and whatever. And so this is what I'm going to talk to you about today. And I just want to bring to your attention that I'm basically stealing work from my graduate students and researchers. Pete Whittington, my PhD student who's finished now, Mazda, who's a researcher who's doing some modeling, and Melissa, who's trying to finish. I hope she will. And I also need to mention Scott Ketchison, a current PhD student of mine, who spent a couple of years working here as my technician. And as it happened, Mike was Mike Waddington's field assistant. That's how he cut his teeth as an undergraduate. So the story goes. So here's the De Beers Victor mine. It's a pit. The ring road around here is 1 kilometer in diameter. And this is 2007. It's in the early days. They've done some stripping, and they've started to expose the kimberlite pipe, which is around in through here. And then the mine camp, at the time, it had about 800 people in it during construction. And they dumped the water into a fen in through here, and the sewage water. And now have a student, Colin McCarter, who's examining those issues at the site. So work goes on. We're interested in what the impact of the mine would be, because the mine obviously requires some dewatering, and so there's a ring of deep wells that go down a couple hundred meters here, 18-inch diameter wells, in which they're pumping water out, and the water is then flowing in from the surrounding area, and there might have been some impact on the peatlands, and so this was the reason why myself and my group were there to examine that. The work was generously funded by De Beers. We used their helicopters about 10 times more than we had budgeted for, and in a collaborative research and development grant with CERC. So the yellow line up in through here is part of the area that we monitored intensively. It's all peatland, and it stretches between 2 rock outcrops on the either end of this. You can see from the landscape that there's a lot of water here. I said that it's 90+% peatland, and some of these are peat pools, peat ridges, and there are various bogs and fens that I'll point out as we go forward in a moment. So I did set a few objectives for this. We wanted to characterize the whole system more broadly, what the impact of mine pumping would be. And one of the things that we were counting on, or I say we in that De Beers in their explanations to the regulators, were that these marine sediments that underlie the area are going to limit the amount of leakage from the peatlands into the bedrock underneath and hence protect it somewhat from desiccation. And then there's lots to learn about the different wetland types here, and in particular looking at the impact of dewatering on bogs and fens in this, and how they'd respond in the short term, and what that means for the longer term when they switch the pumps off. So the Victor project is about 80 kilometers inland, just adjacent to the Attawapiskat River, in through here. And we were, what we wanted to do is to instrument as well as possible, given the difficulty of access in this site, a transect, which that previously showed the yellow line. It's right in through here, and it falls within the boundary of a creek, which has some confusing names, but basically there's a North Granny Creek and a South Granny Creek, and the South Granny Creek is actually right here, and the mine got in the way, so they moved the creek out through this way, and then the northern branch of this creek, which is in this watershed here. So this is North Granny Creek, and then it has two main branches, the north and the south, so north-north and south-north. Anyway, it's a little confusing. And this is a very low gradient landscape, and so there are some difficulties in establishing watershed boundaries. Fortunately, we, as part of the grant money we received from CERC, had LiDAR flights flown over quite an extensive area here, which has allowed us to do some very interesting analysis. But for the purposes of this, it just allowed us to identify the watershed in through here. So the peatlands in the area take a variety of very interesting forms, and the light's not great on the bottom left here, but I think you can see on the top side here, there are lots of ridges and pools in this system, and that depending upon the nature of the system, the ridges may start to organize themselves in a fashion which will begin to hold back water. So you can see in the bottom in through here is a fen system, a fen water track system, in which ridges align in this set of parallel rows, and they retain the water somewhat, and they'll also conduct the water when the system is very wet. And then there are other areas in through here. This is at the top of a dome of peat, which has accumulated over the last 5,000–6,000 years. It's flatter than the rest of the landscape, and so that the pools kind of take on this disorganized, erratic fashion. But nevertheless, there's a lot of water in the environment. And you can see that in through here, this is the fen water track. Here's a fen in through here. And somewhere in the fen, you get these bogs which develop. They might develop because of thermal processes, so they're ice mounds. And you can see that its presence in through here is interrupted the water flow, and then there's this little tail that goes back in through here. And it's really just indicative that very subtle changes in the hydrology of these systems has a big impact on the character of the system, which evolves. So here's a diagram from the planning stage of the mine, and so the mine itself is proposed to be a little over 200 meters in depth. And it cuts into a variety of bedrock types, and the uppermost units at least are limestone, and the fractured limestone, it's very permeable, and so that by pumping the water out of this, and so here's the pumps in through here, they're inviting water to flow back in from the bedrock, and that water's got to come from somewhere, and it's going to come, some of it's going to come along the regional gradient, but a lot of it is going to leak down through these peatlands into the bedrock. And so the dimensions of the impacted zone is going to depend upon the rate of water recharge or percolation through these layers. The less percolation that can occur through this marine sediment layer, the larger the area has to be able to produce the flow which they're pumping out of this pit. And the amount of water which is being pumped out turns out to be about 85,000 cubic meters per day. So it's a lot of water that goes off to the Attawapiskat River, in which case it's a drop in the bucket of that very large river. But nevertheless, we have a lot of water pumped out of this, and so we're interested in the interaction between the peatland and the dewatering or depressurization of the aquifer below. And just to point out that this is not drawn to scale. This is a couple hundred meters. The peat is about 2 meters thick, and the marine sediment is maybe 8 to 20 meters in thickness. So we have some data courtesy of the De Beers monitoring program coupled with our own, and there's a series of a couple of dozen bedrock wells in the area. And this is showing the water, the depressurization or the drawdown cone in the limestone aquifer beneath the peatlands. The peatlands, to some extent, remain saturated because they're perched on that layer. But you can see that in and around the mine here, so this is around 2012, the mine is a little over 100 meters deep, and so that's where the thickness or the drawdown is most intense there for dewatering. And it goes out maybe 4 or 5 or 6 kilometers, depending upon the direction that you go, and it reflects the characteristic permeability of the underlying aquifer where that drawdown occurs. But you can see it's extended out over our watershed, over the North Granny Creek watershed, and so we expect to see some impacts on the bogs and fens that are occurring. Courtesy of the mine geologists, they produced this geomagnetic image, and it's showing the area. The mine pit is down and through here. Our transect is here. And the colors represent the bedrock, depth of bedrock. And so that the reddish areas are where the bedrock is very shallow, and the yellow is where it's kind of intermediate, and the blue areas are where it's quite deep. So we tried to span a range of that across where we took our transect. And that in some locations, this bedrock is so close to the surface that it actually protrudes out through the surface. And here you can see one of these rock protrusions or an outcropping bioherm. We use the word bioherm. They are ancient coral reefs, which is fractured limestone sitting directly on top of the underlying limestone layer. And so we have this system, which is quite complicated here. This limestone goes up to the surface. We have these marine clays, or they call it clay. It's actually not a clay. It's clay size, but it doesn't behave like a clay. And it's overlain at the top by peatland for a couple of meters of thickness of peat. And there are some discontinuous layers of sand. So the issue is that these being highly permeable, we were worried that these might act as drain nodes in the landscape, and that water would flow towards these and then down into the aquifer. So we're quite interested in what the potential role of these bioherms was. And so that will be the first part of my talk in through here. So to orient you a bit more to the research site that we had intensively, we had this north bioherm in through here, and that's actually this one, which is shown right here. It hasn't been struck by lightning. The trees are not burned off. And so it's, our transect expands from this bioherm across a bog area here in the lighter, and here's a bit of a fen water track. You can see it's draining this large domed bog, and the water kind of moves down this way towards the north branch of North Granny Creek. In the interfluve area, there's another bog, and then another fen area carrying water down, another bog to the bioherm. So this area up the top, if you remember back to that geomagnetic image map, is where the bedrock was quite shallow, and so that we expected this to be a zone of enhanced recharge, or an enhanced recharge zone. And it happens to be where all these bogs are sitting. Now, one thing you have to remember is that prior to mine dewatering, there was almost no vertical gradient, so that there was a very gentle horizontal gradient. There's not a lot of incentive for water to move up and down. So these peatlands were quite happy sitting up in through here. With the depressurization of the lower aquifer, then there's a potential that this would become an enhanced recharge zone. And here's just a picture of the north bioherm right in through, right at the edge. So there's a little bit of rock sticking out. And I can barely see that myself, but the bioherm is sitting up in through here. And then just to look at it from the ground, these things are just a couple of meters, maybe 5 meters high. It's like a mountain when you're out in the James Bay lowland, and you can stand up and you can see all around, but really they're not that profound to look at from the ground. So here's a hydrograph of the bioherm. This is the north bioherm shown in through here. at the beginning of, well, just prior to mine dewatering. It started right in and around in through 2007 in earnest. They did some testing in before that. And I want you to contrast that line with this one here, which is a control bioherm, which was sitting about 20 kilometers out further to the west, in which there are no gradients being imposed by that mine dewatering. And so what you can see in the North Bioherm, that the dewatering of the aquifer is indeed having an effect over this 5-year period, and that the water levels are declining steadily. And the other thing is you can see a very distinct seasonality, so that in the spring period there is water recharging as water is mobilized on the surface of the peatland flowing towards the bioherms, and it's, or recharging elsewhere, not just in the bioherms, but this is kind of reflective of the bedrock in general in that vicinity. And that we can see that there's a great deal more interaction then with surface waters in these bioherms than there was previously. And this sub-inset in through here is actually the control bioherm shown at a very different scale. It has some seasonality, but it's negligible compared to what is happening in the current bioherm. So we instrumented the North Bioherm here with a series of well transects and a bunch of other these bioherms in this enhanced recharge zone. And we wanted to see what the water table conditions were like there. And so we have a series of graphs showing here distance out from the edge of the bioherm, the zero, out to about 50 or 60 meters, and then depth into the peat in that zone. And what we can see in all these transects is a very clear trend that the water table is being drawn down near these bioherms as a consequence of dewatering of the deep aquifer, so that water is draining from the peatlands in towards the aquifer. But one of the things we know about peatlands is when the water tables drop, the water table and the saturated zone is residing in more decomposed peat. And that more decomposed peat has a fairly low hydraulic conductivity, and so that the water isn't going to be gushing through that lower layer of peat, and it maintains itself so that by the time you get to 20 or 50 or even 50 meters out, or sometimes closer, you're not seeing a large impact in terms of the dewatering of the peatland as a consequence of drainage through the bioherm, at least. Now, there are a few of the well transects and a couple of the wells in some of the well transects which had kind of a different pattern, in which there was either an empty pipe or a very low water level at some distance fairly close to the bioherm, but not in the bioherm itself, in the peat adjacent to the bioherm itself. And so that we were wondering about this at first, but it seemed to make sense afterwards when we began to think about the structure of these systems. And so that there's a zone here in which, at some point far out, it's sitting over these marine sediments, and it's reducing the water percolation downwards in the system. But you get to a point in the system where the peat is lying directly over top of the bioherm. And that these bioherms are fractured, but the fractures are not continuous. They're exposed in some places, and in other places, it's not. And so that what our hypothesis is that in locations where the peat is sitting directly over a fracture, or in the cases where the marine sediments are thin and overlying a fracture, then we get leakage into the thing, and we get these funny patterns like this. So on the basis of the field data, we can make some calculations, and that using Darcy's law, we can measure the slope of the water table gradient in through here, and that we've estimated that the Darcy velocity, at least, is about 1 to 2 millimeters per day. That's not huge, but anyway, they are draining and over a radial area. And these bioherms are quite common in the area. They might represent, I don't know, maybe 2 to 5% of the peatland in the area. And out further, where we have thicker marine sediments, we can also measure the vertical hydraulic gradients using nests of piezometers. And again, through Darcy's law, we can estimate the water flux, and that it's somewhat more, maybe 2 to 4 millimeters per day, depending upon the thickness of the marine sediments and their hydraulic conductivity and so on. So I want you to put that in context of the precipitation and the evaporation here, which when we take evaporation away from precipitation, we're left with about 260 millimeters of water per year, which can either run off down Granny Creek or recharge into the system. Now, prior to mining, most of that water would have gone down Granny Creek. Now we're setting up a situation where we have well, if we have 3 millimeters per day times 365 days, we've got over 1,000 millimeters of water, which is going to want to go down that way. So the water storage is going to change, the peat is going to dry, and indeed we've seen that. So coming back to this diagram of the drawdown, there's a few other things that I wanted to point out, and that in our watershed here we have, it's entirely bogs and fens with a few bioherms that are located. And what you can see is these areas with the big pools, the darker areas, these are the fens. And the fens are the areas which receive and transmit water from the whole watershed, and that they generally feed into the creek systems. And here's one of the north-north Granny Creek system here, and the south-north starts somewhere in through here. And that they're connected to these fen water tracts, which are the conveyance networks for the system. And between the fen water tracts, we have these lighter areas, and the lightness is sometimes caused, well, it's the sphagnum mosses and the lichens that are dominant in these. And these are the bogs. And they're raised a little bit up above the fens, and so that they're receiving rainwater, and that rainwater flows off, or the snowmelt flows off into the fen water tracts, and that moves down into the system. And so I'm also interested in how these are behaving and how they're responding to the dewatering, which is occurring especially in the eastern part of the watershed. So I have a couple of graphs that I want you to look at. And here we have a graph which is showing the surface elevation, this continuous line in through here, going from the north bioherm to the south bioherm here, so from north to south. And what you can see is that there's in the bog here in the pink, it's sloping down towards the fen area. So here's the bog here, sloping down to this fen water track, and then eventually to one of the branches of the Granny Creek. And then between the Granny Creeks here is this raised bog area again, and then the creek, and then back up through bog into the southern bioherm. The dots that are plotted are the hydraulic conductivity. And if you squint a little bit, you might be able to see a trend that the hydraulic conductivity of the fens, at least in the horizontal direction, is higher than it is in the bogs. And so the dark ones are these 90 centimeter values, and the open ones are the deeper piezometers. But basically, you can see that the fens are better able to transmit water than the bogs, at least horizontally. It turns out that the fens have a fairly low vertical hydraulic conductivity, because they're mostly formed from sedges and things that die like that, and then they form this anisotropic system, which favors horizontal water flow, which doesn't happen in the bogs, which is moss-dominated. Anyway, so what you can see from this is that the fens have a somewhat higher ability to transmit water. And I want you to look now at the bottom. This is, again, a set of hydrographs. This is water table in meters above sea level, and going from 2009 to 2011 here, a number of years of data. And the top two are these systems that are well and gone from the impacted zone. And what you can see, and this is further out to the west, so that it's more elevated. That's why it's higher. And at the scale that's plotted, you can really see no seasonal trend in the bog, and scarcely you can see it in the fen. But basically, over time, they're maintaining their elevation, they're static, they're our reference systems. In North Granny Creek in through here, the fen, you can see, is starting to behave a little bit more as it does dry out a little bit because of the dewatering. And you can see some of the responses in through here. But you can see that the bogs are draining somewhat more. And so that it's kind of hard to see on this scale, but it works out to about, they're declining maybe 30 to 50 centimeters over this period, the water levels in some of our bog sites. And it's declining, whereas the fen is not declining quite so distinctly. And down at the bottom here, you can see the bedrock well that it's being obviously impacted by the dewatering of the aquifer. So I want to just take a moment to try to explain what I think is going on here, in that the bogs, if you'll remember, are these areas that are sitting here. They're isolated. They're not receiving water from anywhere. They're just giving it. So these are the water storage zones, and that the water is moving either downwards, percolating into the sediments, or moving into the fens and the creeks. And so that these water tables are declining because of that increased leakage. The fens, on the other hand, are these conveyance networks, and yes, in the impacted zone, they may be leaking somewhat, but they're also receiving water from upslope, from the upper part of that fen network, And so it's helping to sustain the water levels in those systems. We have some data. These are isotope data, oxygen-18 and deuterium. I'm not going to take a lot of time to explain this if you don't already know what it is. But basically, these are isotopes of water from different sources. And we can tell something about how the system is behaving by looking at these. So that the solid line here is the global meteoric water line. It's how rainfall plots worldwide on average. And that we have some different sites in through here. And what we see is that here the gray triangles are the deep groundwater. And they are plotting on the same line as the as the rainfall, which is indicating that over the long term, and so this has been recharged, I don't know, tens or hundreds or thousands of years ago. These waters are at the same source as the rainfall. And you also see that the bogs here in blue are plotting exactly the same. So what this is indicating to me is that the bogs are still, because this is the current data, are catching the rainfall, and when the water is leaking down through the system and it's recharging the groundwater. And the fens, in contrast, they're taking off like this. They're showing signs of water being held at the surface in that conveyance network, being evaporated, and it's the same water which is in the creeks. And so that, what's happening here, it seems, is that the bogs are the ones that are experiencing most of the recharge. I think you're standing up because you're giving me a signal, right? Okay. All right, so I'm going to move on here so that basically what we're seeing in the bioherms at the end of this system, we can convert the hydraulic gradients, which were in the slide I just skipped, to recharge. And again, we see high recharge in these areas that the marine sediment is thin, and in and around the creeks, it's kind of neutral. So very quickly then, I'm going to go through our final work in the project is relating to some modeling that we're doing. And this is my researcher in my lab, Mazda Kompanizari. And we've separated the landscape out into bogs and fens and domed bogs. In this numerical model, it's down to a couple hundred meters deep, incorporating all the layers of the system. It's been calibrated with about 35 different points in the system, and basically the red is the data. Sorry, the red is the simulation, the blue is the data. And you can see that it fits mostly. There are some issues with it. And we can predict the drawdown cone from this, which is looking somewhat like the one that is from our data, with some anomalies that we're working on. And we hope to be able to use this to project a little bit further into the future. So the mine is about 6 years into its operation. It's going to go for another 6, so we should be able to say something about it. Anyway, so we're able to show, and this is horizontal water velocities, and it's basically showing that the fens water tracks are still conveying water, but the point that I want to show you is that we are going from a pre-mining situation in through here, which is simulated, which is about 25 millimeters of recharge per year, to a system where over this whole domain, the recharge is 281 millimeters per year, and in through here, we're up to over 1,000, so that we're obviously having a system which is drying quite a lot, and remember the water budget in through here. And it's just showing the mine pumping in through here over time. This is over a 5-year period. This is the mine pumping rate, now at 85,000 cubic meters per second. And here's where the water's coming from. This is the peatlands. It's percolating through the peatlands. Some of it's coming from the far end of the system, but the peatlands are providing most of this water. So to conclude then, the implications of this are several-fold. This is still the 2007 picture, but strangely enough, it doesn't look all that much different today. Well, it's going to be a lot of snow today, but in the summertime, and that there's still pools and things which are around the mine, and some of them are full of water, some of them are empty, and that this again relates to this sporadic occurrence of fractures in bedrock, which cause some parts of the system to drain. What we find in this system is that there's a range of vegetation types responding to the subtle water conditions in there, and so that here's a system with a sequence of ridges and pools and things, and that the system is healthy here. It's a pool. Here's a pool which is drying out a little bit, and this dried out pool is going to start growing mosses like are at the edge of the pool, and the edge of the pool might get a little bit drier and start growing a few more shrubs. And the pool here might turn into something like this. So there's going to be subtle changes in the system. But as the system is drying out, these ridges are going to become more prominent and going to have a greater ability to retain water in the system, so that we expect the flow from the creek to diminish. And that if this entire peat deposit drains, and the specific yield is about 2, so we can do some quick math. 2 meters of peat means the water storage release here would be about 400 millimeters worth. Again, here's the rainfall, 260 millimeters per year. When they turn off the pumps, after a couple of years, this system's going to fill up, and there's going to be some subtle changes, but probably not a great deal. And the final point that I wanted to make is that one of the issues that we have of concern here, and in particular to the First Nations community down here in Attawapiskat, are the implications on mercury. And wetlands are great methylators of mercury and making it mobile and toxic. The toxicity in the fish here has been going on decades before the Victor mine, but De Beers coming in here with deep pockets has become a target where mercury has become an issue. So we are wanting to be able to say something about what's happening to the mercury. And what we can say, based on what I've just finished saying, is that instead of the water moving down through these surface water systems relatively rapidly, it's now going to take the long route down through these marine sediments in the bedrock and take thousands or tens of thousands of years to get to where it's going. So maybe a little comfort if your fish still have mercury, which they do. Okay, so I have a few conclusions, but in the interest of time, I'll close here and just make the final point is that after 12 years of mining, they turn off the pumps. Probably when all is said and done, there's not going to be a huge impact in the area.
Okay, okay, very interesting. We can have 1 or 2 questions for John, if anyone has a question. Any question? Okay, we can move for the next talk. And thanks again, John. I have a small gift for you too. Thank you so much.
Thanks, Bernie.
Yeah, great. Thank you.